Institute. A little bit about me. I'm Steve Bellavia. I'm a volunteer. I've been a volunteer here for about 15 years. I've been a member since the 1980s. I work full-time at Brookhaven National Laboratory. I'm on many physics and astronomy projects there. I worked 7 or 8 years on the Large Synoptic Survey Telescope, now called the Vera Rubin. I'm working on a quantum entanglement interferometer there now, and you'll see a few other things in the talk. I also teach at night at Suffolk Community College. I teach physics, astronomy, and engineering there, and I'm going to start the talk. I'm going to thank you for being patient. We were just waiting for the last stragglers to get here and come in. So the invisible universe. So first I'm going to start off by saying I'm also an amateur astrophotographer, and this is my picture of the Horsehead Nebula, and it's not bad, you know, but then when you look at the Hubble, you know, that's a lot better. What am I going to show next? Who can tell me what's going to be next?
James Webb.
The Webb, right? James Webb. Well, James Webb is going to be amazing. Like the detail is going to just be like, you know. I don't think that James Webb has done the Horsehead yet, but it will be better. Trust me. I had to do some comedy. Okay, so what is invisible in the universe? Well, lots of stuff. It's anything you can't see. You know, we can't see air. It's there, and we can't see radio waves, gravitational waves, X-rays, infrared, dark energy, dark matter, magnetic fields. And I could talk about all of these, but we don't have that kind of time. So I'm going to narrow it down to just two. Tonight, we're going to talk about radio waves and gravitational waves. These are things that are invisible to your eye, but astronomers are using to learn things about the universe. So what are radio waves? Well, they're actually light. Radio waves is just like the light that comes into your eye, with the difference being that you can't see it. It's light you can't see. So here's the electromagnetic spectrum. You might have seen this before. But on the far left, the longest waves or the lowest frequencies are radio. And then you have microwave, like you cook your food with. Then you have infrared. Then you have the visible spectrum, which is very, very narrow. I've blown it up there on the bottom so you can see it. But, you know, the Roy G. Biv, the red to violet, is a very narrow part of the light spectrum. And then you get shorter and shorter wavelengths and higher frequencies, ultraviolet, X-ray, and then gamma rays. So all of this is the same phenomena. It's all light. It's all photons. But our eyes aren't able to see all of it. So our eyes are, you know, it has a lens and rods and cones, and there's a retina and an optic nerve that brings these signals to your brain so you can figure out what you're seeing. Is not a radio receiver, right? Our eyes don't pick up radio waves, right? They are still the same phenomena, but your eyes can't detect radio waves. So a little history of radio astronomy, and try to remember these, because when I give out the test later, I don't want you writing the dates wrong or anything. It starts in 1867 with Maxwell and Maxwell's equations, and he predicts radio waves. This is just mathematical predictions. About 20 years later, Hertz, and you probably have heard the term Hertz, like when a radio station is 103 megahertz. That's who it's named after, Hertz. He demonstrates that Maxwell's predicted waves are real through experiments. He actually creates radio waves. And in 1897, Marconi, the inventor of the radio, wins a Nobel Prize in 1909 and shared with Braun in recognition of their contribution to the development of wireless telegraphy. They were using the telegraph. They were basically making sparks and sending them long distances. This is how people communicated back then. The reason Hertz and Maxwell did not get a Nobel Prize is the Nobel Prize didn't start yet. Because Maxwell's equations, Einstein used them. You know, I think like there's probably a couple of dozen Nobel Prizes because of Maxwell. But he was before the Nobel Prize started. In 1932, Carl Jansky of Bell Labs is trying to find out why transatlantic phone calls down in New Jersey. He's working there, and his boss says, people are complaining they're paying big bucks for these transatlantic phone calls, and they're staticky. Go find out why. So he goes out and tries to find the source of the static and realizes it's coming from the universe. And he wins a Nobel Prize. In 1964, Penzias and Wilson, also down in New Jersey, discover the cosmic microwave background. This is the remnants of the Big Bang. This is, if you've ever heard like an ambulance or a fire engine siren go by, as it comes towards you, it's a high frequency. It goes, then it goes down, and it stretches. The stretching of the waves is because as they're moving away from you, the wavelengths are getting longer and longer, lowering the frequency. Well, 13.8 billion years ago, when the Big Bang happened, what we see now, 13.8 billion years later, is that stretched out so far that it's become a radio wave. And we can see the entire universe when it was born 13.8 billion years ago. And they won a Nobel Prize. So here's Jansky's, they called it the merry-go-round antenna, a little different than the big antenna that's up here, but similar in principle. And he would move it around trying to find where the static's coming from for these phone calls. And what he noticed is that they seemed to be on a cycle, and at first he thought it was 24 hours. That every 24 hours was when the static happened, and he said, oh, 24 hours, that's got to be the sun. But then when he'd point the antenna towards the sun, or even in the daytime, was not when he was getting the biggest signal. It seemed like he was getting the bigger signals at night, and being a very good engineer, he looked at his data carefully, and it wasn't 24 hours. It was 23 hours and 56 minutes. Does anybody know the significance of that? Why is 23:56? Why isn't it 24 hours? Well, that's how fast the stars move. I don't know if you know that, but the stars rise and set 4 minutes faster every day compared to the sun. And why is that? Is the Earth just spinning in place? Are we just standing still spinning? No, we're moving around the sun as we're spinning, and it just so happens we're moving in the same direction we're traveling through space, so the stars get a 4-minute boost. The stars move 4 minutes faster every day, and if you take 4 minutes times 365 days, that's a full cycle. It's the reason the constellations change, right? We have Orion in the winter, Sagittarius in the summer. The sky is constantly changing because we're moving through space, and that's 4 minutes a day. So then he says, wait a minute, if the stars are moving at this rate, I must be listening to the stars. And he discovered radio waves are coming from stars, and then when he pointed his antennas to the heart of our galaxy, Sagittarius A, is when he got the biggest signal. And him and an astronomer guy got the Nobel Prize for that. So that's Carl Jansky. They've named arrays, and there's a unit in radio power called the Jansky, so he's got a lot of things named after him. And then Penzias and Wilson, they built a horn antenna about 10 years later, and picked up what they thought was a steady signal of the background of the universe. But later on, more advanced antennas realized there's actually some structure to it. We'll talk about that. So how does a radio telescope work? Well, it works just like a regular telescope. Light comes in, except it's radio light, hits a secondary, kind of like what would be a mirror on like the big reflecting telescope that's over on the lawn there. And then it gets converted into an electrical signal because it's radio, so you can't see with your eyes, and from the electrical signal, they can reconstruct the data that you're seeing, and we can even make pictures from it now. But it's really just like a regular telescope, except the only difference is that it's radio light and not visible light. So that's how a radio telescope works. So why am I telling you this? Well, it's as if you went to a concert and your ears could only hear like 5 notes, like somewhere between the flute and the oboe, and you're missing the rest of the concert. This is what the universe is doing. The universe is playing in all these frequencies, but up until, recently, like maybe 100 years ago, even less, we've only been seeing a little part of it. We've been missing most of the concert, but now that we've realized this, we're going out and building telescopes that can pick up the light in all the things. So here's some examples of radio telescopes. So this was the biggest in the world. This was in Puerto Rico. It's actually collapsed, and they're talking about resurrecting it, and actually Brookhaven Labs is actually involved in a team that might try to resurrect it. But this was a 305 meter, or a third of a kilometer, radio telescope, but it didn't move. It waits for the sky to go by. So it actually can't really track the stars, but it could pick up signal and data. And it's done a lot of great stuff. Like Arecibo was the first time we realized that Mercury was actually spinning around the sun. We thought it was tidally locked to the sun, the same way the moon is tidally locked to us, right? We only see one face of the moon. Well, they thought that the sun could only see one face of Mercury, and the reason was when they were observing it visually, they would see a feature on Mercury, and then in Mercury, half of a Mercury year, they would see that same feature still facing the sun. What they didn't know is when it got behind the sun, it was doing another spin. It was tricking us. It would spin once in front of the sun and again behind it, and since the radio telescope didn't care about looking directly at the sun, because it wasn't going to burn out its eyes like we would a telescope, it found out that Mercury was spinning. So that's a cool discovery from Arecibo. This is now the biggest telescope in the world. It is half a kilometer across, which is really big. And this is in China, and it's called FAST because it stands for the 500 meter aperture spherical telescope. So this is now the largest radio telescope in the world. This is the largest steerable radio telescope. This is in West Virginia. It's part of the National Radio Astronomers Organization in West Virginia, which is where the sort of headquarters for radio astronomy is for pretty much the world. And this is the Green Bank telescope, and this is an interesting telescope. It can track, so it can actually follow whatever it's studying. But another interesting thing is if you go to visit this, they don't let your car past a certain point because your car is most likely not a diesel, and the sparks from the spark plugs and the engine's noise will interfere with the telescope, so they shuttle you up there in a diesel bus because the diesel doesn't affect the radio telescope. And I've been there. It's really a cool place. So you go up there by diesel, and there's actually all rules for people that live in the area about how much radio noise. Like, they wouldn't be allowed to have this. You know? So there's only so much radio noise you can make if you live there. This is the Jansky array, named after Carl Jansky, and this is in New Mexico. And this is 27 telescopes, so it's 9 telescopes on 3 arms like a letter Y, and they can move in and out if they're studying different wavelengths of radio. So further out is longer wavelengths, closer in is shorter wavelengths, and they move them in and out, you know, sort of motorized. And so this was the largest array telescope, and its cool thing about radio telescopes is the 27 telescope will act like as if it was the diameter of one big one at the extent of that letter Y. Like if you circumscribe the circle around the Y, it's as if it was one big giant telescope. But this is even bigger. This is up in way up high in Chile, in the Atacama Plains, in the mountains. And these are 12-meter antennas, and there's a bunch of those at 5,000 meters, which is like 17,000 feet. When you get up there, you actually get some altitude sickness and might need oxygen the first couple of days until you get used to it. But this is way up high on the Earth in an area that has very low radio noise, and this is the largest array telescope now. But this is the largest array telescope in the world. This is the Event Horizon Telescope. This actually uses ALMA and uses Jansky and uses a whole bunch of other radio arrays to act like a telescope half the size of the Earth. Right? This is actually kind of putting them all together, and it's done very carefully with GPS and other fancy electronics that make this act like a giant, giant telescope. They're using atomic clocks and GPS systems to get them all synchronized so that it works. And there's a reason it's called the Event Horizon Telescope. Does anybody know what this telescope's famous for? What did it do? Very good. Somebody said a black hole. That's what it did. Our first, that's how big the telescope is. Our first picture of a black hole was April 10th, 2019. This is not a black hole in our galaxy. This is a black hole in a galaxy called M87, Messier 87. And they picked to do that one first because that black hole is actually bigger than the black hole in our galaxy and easier to see because our black hole is blocked by our own galaxy. It's kind of like in our own way. So they did this one first. It's larger. And the reason the telescope's named the Event Horizon is that's what they call this area of glowing gas around the black hole. So you actually can't see the black hole itself. The photograph of the black hole is really a photograph of the event horizon. Right? So that's the area that gets this highly energized gas or plasma. It's actually very energized. That's circling the black hole and being energized because of the rapid velocity and going round and round the black hole itself. So that's the event horizon, and outward is what we can actually image with the radio telescope. And of course it's an image that's converted from radio frequencies to visible so you can see it. And just to give you an idea of the black hole that's in the center is 1 billion times more massive than our sun. That's 10 to the 9th more massive than our sun. And the size of the event horizon, or the area around the black hole, is 42 micro arcseconds. So let me explain what that is. So a degree is 1/360th of a circle. An arcsecond is 1/3600th of that. A micro arcsecond is 1/1000th of that. So this is a tiny spot in space. This is the smallest object any telescope on Earth has ever imaged, and the reason they're able to do it is the telescope is so large in aperture and diameter. It's the size of the Earth. So this is the smallest object ever imaged. But they did do our black hole. This was done May 12th, 2022. So this is only 3 months ago. And they got our own black hole. So this is nice. This is the black hole in our galaxy. And pretty much every galaxy except for a couple that are weird, like triangular, have black holes in the center. So this is the black hole in the center of our galaxy. A little harder to do, and the reason they did it second. This is supposed to be a video, but it's probably not going to play. I knew that was going to happen. So let me see if I can get it to play. So small technical difficulty here. Can't get it to play. Sorry, but I'm not going to waste time messing around. But what was nice with this video, if you could see it, and you could go online and find it because it comes from the Center of Astrophysics, Harvard and Smithsonian. This black hole is spinning very slowly, and ours is the event horizon or the gases around it are spinning much faster because it's smaller. So the smaller black holes actually have higher velocity gases going around them and with more energy. So even though the black hole is smaller, the stuff around it's got more energy and going faster. So it's just kind of a cool thing that our black hole actually has sort of faster stuff going around it. And that's Sagittarius A, that's in Sagittarius. That's the direction of that black hole. So what are some radio sources in astronomy? Well, we just talked about black holes. The sun itself is a radio source, not as loud as the center of our galaxy, as Carl Jansky found out. Jupiter and its moon Io is a source. Supernova remnants left over from stars that exploded are radio sources. Pulsars, which are pulsating stars from galaxies that have sort of collapsed on themselves. Star-forming regions like Orion Nebula, where stars are being born. Radio galaxies is actually galaxies that put out radio waves, and we already talked about the cosmic microwave background, and we're going to talk about it a little more. So the sun. This is the sun at around 4.6 gigahertz, which is just about your cell phone. This is like cell phone frequency. And what you can see from this image, converted from radio waves to visible light, is that the sun is not one uniform thing. There's hot spots, right? I mean, look at the red is 1,000,000 degrees Kelvin, the green is 30,000 Kelvin, and the blue is the surface of the sun, which is 6,000 Kelvin. So the sun has different temperatures, and this would be impossible to find out with visible light, or very hard to find out. Nothing's impossible, but much better done in radio waves. Jupiter is a weird thing. Jupiter has a very strong magnetic field like the Earth, in fact, much stronger than Earth's. And then this moon Io has these volcanoes that spit metals and sulfur into its atmosphere. And since Io is rotating around it, this interaction between the magnetic field of Jupiter and the stuff coming out of Io's volcano actually creates sort of like a klystron, like a radio signal generator. And this is a very loud signal. This is actually very low, though. This is like in the low FM range, is Jupiter and Io. So that's an interesting radio source. People can build their own radio telescopes. Cygnus A, this is, it's in the constellation Cygnus, but not really. Like the stars we see in Cygnus, in fact, look at that, what perfect timing. I don't know if you know Cygnus, but Cygnus is a swan. It's got a long neck. That's the head of the swan. These are its wings. Right? And that's its tail, which is deneb, which means tail in Arabic. This is the swan. In Cygnus is this thing, but it's not really in Cygnus. The stars here are from maybe like dozens to 1,000 light years away. This is 600 million light years away. So it's really behind Cygnus. It's way out there. I mean, this is not, it's in Cygnus in direction, but it's not in the stars. It's not in our galaxy. This is other galaxies 600 million light years away, meaning that the radio light that's getting here now left there 600 million years ago traveling the speed of light. So this is, once again, this is from the Jansky array in New Mexico. If you could see in radio, which you can't, but if you could, at radio frequency, cell phone frequency wavelengths, this is what you would see in the sky. This is actually a nice picture taken in New Mexico of the sky. And what do we have here? Well, we've got on the upper left or middle left, we have a supernova remnant. Then we've got a star-forming region, which is basically ionized hydrogen, which is the most abundant element in the universe. And then we got 5 billion light years away, a radio galaxy in quasars. 5 billion light years. So here's a weird thing to think about. And don't think about it too hard, though, because it'll hurt. If somebody was there looking back at us, we don't exist. Our sun hasn't even formed yet. We don't even have a sun yet. Forget about the solar system. Right? So that's kind of weird that we can look at them, but they can't look at us because of this weird time thing that happens across the universe. So that's what the sky would look like in radio light. And this is the cosmic microwave background. And this is now more recent data that shows that the background from the Big Bang isn't uniform as Penzias and Wilson thought. There's actually little subtle differences. There's these little tiny differences in temperature. There's everything in sort of in the electromagnetic spectrum sort of represents a temperature. And radio is very cold, and gamma rays are very hot. So we're talking like millikelvin difference, like 0.0002 Kelvin difference from the red to the blue. But what it shows is that the universe is not uniform. There's actually places where there's more likely to be galaxy formation and others where there's less likely to be galaxy formation because there's less matter there. And this is what the cosmic microwave background tells us is where was their structure. So galaxies tend to form in these sort of filaments in the universe, and this is sort of showing that. So we kind of have like a baby picture of the universe showing where the galaxies will form when they form. So it's kind of neat. So this is a very important area of astronomy and mostly cosmology, which is a study of pretty much the universe overall. And I'm right here on Long Island. This is in one of the old sumps at Brookhaven National Lab in Upton, New York, right off William Floyd Parkway. And we built an antenna there that studies a special part of the radio spectrum. And this is the radio telescope with some of the people that worked on it. And the special part of the spectrum is 21 centimeter hydrogen. There's a level of hydrogen, and I mean like level, I mean electrons orbiting sort of the nucleus of hydrogen. When they jump shells, when it goes from one level to another, emits photons, and that's how all light is basically formed from elements, right? There's visible spectrums, and there's these invisible to human eyes, but to radio light, you can see it. So this is 21 centimeter hydrogen, and it's special because it represents a sort of part of the universe we haven't been studying up until now. So I mentioned I'm an amateur astrophotographer. Here's a picture I took of 3 galaxies. There's actually a 4th, but we're not going to talk about that one. But here's M82, the Cigar Galaxy, M81, which is called Bode's Nebula, even though it's a galaxy. But astronomers refuse to change the name of something no matter what happens. It's the same name forever. Unlike the marine biologists that finally decided to call a starfish a sea star, but astronomers will never do that. And then here's NGC 3077. And my question to you is, do you think these galaxies might be interacting with each other gravitationally, or is there any matter exchange? Can you tell from this picture if these galaxies might be interacting? And these galaxies are about as far from each other as we are from Andromeda and the Triangulum Galaxy, which is our closest neighbors of galaxies that are like ours. So does it seem like they are? Well, let's look at it in 21 centimeter hydrogen and see. Oh my God. These galaxies are interacting tremendously with each other. There's all kinds of tidal streams and material being sucked off from one galaxy to another. These galaxies are intimately interacting with each other, and unless you study it in 21 centimeter or 1420 megahertz light, you don't know this, so I created a little animated GIF that I hope plays. There you go. So there's my wimpy little visual picture superimposed with the radio light picture, and it really shows how much we can learn about the universe using things beyond the visible spectrum. And this is sort of the whole reason for the Invisible Universe talk. It shows you what can be done when we look outside this narrow spectrum of visible light. Radio telescopes. I forgot to bring it out. I have it in my car if you want to make one of these, but you can build your own. It's called the Itty Bitty Radio Telescope. I did not design this. You can go onto a website called the Itty Bitty Radio Telescope, and you can build one out of a discarded satellite dish. It's not expensive. If you get the satellite dish for free, like I did, because it was mine, I don't use it anymore, the receiver is $7.90. You save 40%, it says. So why do they sell this? Does anybody know why they sell these radio signal detectors for $7.98? Anyone here ever done any camping? There's a lot of people that go camping and want to watch TV in their RVs and in their tents. And this is a satellite finder. This will help you find, Sirius and DirecTV and all the other satellites that are somewhere about there all the time. They don't move, they're geosynchronous. So that's why they sell these, and that's why they're so cheap, because they sell a lot of these. A lot of people go camping and want to watch television. And then you need a power supply. You can use batteries. I have batteries that switch. So you can build your own radio telescope. So here's the summary of the radio part, is that your eye is not a radio receiver. All great radio astronomy discoveries are made in New Jersey. A satellite finder is $7.99, you save 47%. And 21 centimeter hydrogen gets through more schmutz than visible light. It makes it to the surface of the Earth. So that's the radio part. Let's talk about gravity waves. What are gravity waves? Well, Einstein predicted this. These are ripples in the fabric of space-time. So Einstein thought differently than many people, and thank goodness for that. And realized that space and time are one thing. They're not two different things. They're kind of connected. and that even the gravity of Earth is just a dent in space-time. The gravity waves themselves, they transport energy as gravitational radiation, not electromagnetic, but gravity radiation, as a radiant energy similar to electromagnetic radiation, but there's no electrons involved in it. This is strictly just mass and gravity. It's pretty much putting dents and ripples into space. But it has to come from, if you're going to get these waves, they have to come from very massive accelerating objects, generally objects that are orbiting each other, because that's a form of acceleration, centripetal acceleration. And it's basically neutron stars or black holes. That's what causes them. And oddly enough, they do travel at the speed of light, and I'm not sure what the relationship is between gravity waves and light, because they're not the same thing. They're not light. They're their own thing. So how do you measure? So I have to talk about how you measure distances, and this has very little to do with the universe by itself. This just says that if you have two waves, and you add them constructively, you'll get a bigger wave that could be twice as the amplitude. And destructively, if you put the waves out of phase, in other words, you take a peak and line it up with a trough, you'll get nothing. And this is how we measure distances. This is what Michelson did and created the Michelson interferometer. You interfere and can measure very, very small distances. And interferometers can measure, down to nanometers or less. So somebody thought, well, if the entire space is shaking, how do we measure it? So they decided to build this giant interferometer that has two legs, so that if the universe kind of ripples this way, that this leg should move a little compared to that one. In other words, the length of the entire leg of the interferometer is going to expand or contract as these gravity waves pass through it. And they're going to use the method of interferometry, of using interference of waves by shining a light down. We're going to make the mass that moves a mirror, and we're going to see, does this one change from that one at any point in time? Right, so this was an idea that I think started in the 1970s. And here's one of them. This is the one in Livingston, Louisiana. And these are really, really, really long legs of vacuum tube that a laser is being shined down. And at the very end is this mirror. And then there's another one in Hanford, Washington. These things are gigantic. These are the biggest interferometers ever built. And they suspend the mirror. And that's what they call the mass. That's the thing that the universe, the space-time is shaking. And we're going to see if it moves, right? We're going to see if this mirror moves relative to that one. And if it does, it means that something happened, right? And the way they do it is amazing. It's an engineering feat. It's a quadruple pendulum, so that if a truck goes by, or if there's an earthquake or a hurricane or something, it's not causing the mirror to shake. The only thing they want to cause the mirror to shake is the space it resides in, right? So kind of think of it like an earthquake, but instead of the earth shaking, space itself is shaking, right? The space you're in is shaking. So this is, like I said, it's an engineering marvel. It took them, I think, like 30 or 40 years to finish building this whole thing. And they detected something. Back in, let's see, what was the date? I forgot. It says it somewhere. Oh, on the top. No. Nice. I have where I wrote it. September 14, 2015, they got the first shaking of space, and modeling and using lots of astronomy knowledge. They were pretty sure it was a black hole merger. That two black holes were orbiting each other, and they have computer models to sort of simulate this, and eventually collapsed into themselves. And we've picked it up. We got it in our first gravity wave detection, and it was all over the news, all over the world, that they got it. And it was kind of like, they call it a chirp. It's actually in like an audible frequency, if you could actually hear it. Of course you can't. But it was in the order of like hundreds of hertz. And they could see them orbiting each other and orbiting, and then boom, nothing, because now they're one bigger black hole, a larger black hole. Not quite twice the mass. Let's just say they were equal, because they lost energy in the orbiting and collision. So twice the mass minus the energy they lost during the collision, which is what we're detecting. So think about what LIGO's measuring. It's 1/60,000th, right? It's 16, lots of zeros. Or another way to look at it, it's this many zeros with a 4 of the diameter of a human hair. This is the most sensitive instrument ever built on Earth. It's crazy when you think of how accurate it is. And they went through rigorous testing to make sure they weren't picking up some other vibration. And in fact, they even do runs on purpose where they don't tell the physicists where the data is coming from. and let them figure it out, and then decide if they've passed or failed the test, right? So, and they were actually doing an engineering one when they discovered this first black hole merger. They weren't even like fully operational. So what have they done since September of 2015? Well, this is, I don't expect you to read this, but it is on the test. These are all the discoveries that have been verified. There's lots of discoveries they're not sure about, but these are the ones that have been verified. And they all start with a GW for gravity wave, with generally the date, the time that it was discovered. That wasn't a gravity wave, that was a motorcycle. That was a motorcycle. So these are all the discoveries that they've made so far. They've made a lot. And this is them pictorially, the discoveries of what they think they were. So a lot of them are neutron star mergers. Some of them are neutron star black hole mergers, and some of them are black hole mergers. And by the way, these aren't the biggest black holes. These are ones that are only 80 solar masses, and I say only because remember that M87 one was a billion solar masses? So these are the smaller ones. These are picking up the gravity waves. That's sort of like the wavelength or frequency range of LIGO, is these sort of smaller black holes and neutron stars. So this is a representation of all the discoveries so far. But is there any way, because people like, yeah, okay, you've got all this interesting data and it's all this weird mathematics you have to do with the data you get, but can we see it, right? I mean, let's get back to visual. People like when they can see stuff. So, so these are using LIGO, Hanford, Washington, and Livingston, Louisiana, where they think it could be in the sky. And as you can see, some of them are really broad, because when you've only got 2 points, it's hard to triangulate anything. But they also have, there's other interferometers around the world. There's one in Italy and more being built. But this one that I highlighted is sort of the smallest part of the sky, and maybe possible to look for stuff, right? Maybe we should be looking there. And when I say looking there, I mean like a second after they get this signal to tell other observatories, hurry up and look in this part of the sky, which is a big part of the sky still, but quite small compared to the other ones. And they got it. They got the first visual confirmation. So they used, you know, the 2 LIGOs in the United States, and they used the one from Italy. And, you know, using the exact time of detection and GPSs and all this other stuff, they could start getting the place where it came from. And there it is. There is a light signal, a visible light signal, from the collision of 2 neutron stars. And it was confirmed to be an NGC 4993, which is a galaxy, you know, pretty far from Earth. And it's interesting, the data from the Italian LIGO didn't get any signal, and that actually helped them find it, because not getting a signal also helps you triangulate. So this is the very first time in human history that we've gotten a electromagnetic confirmation with a gravitational interaction. I mean, when you think about, you know, in less than 100 years from when Einstein predicted this is possible, right? So, you know, think about what humans have done. I like to think this analogous to, in 1904, the Wright brothers flew an airplane, and in 1969, man was walking on the moon. Right? So we do great stuff. So what's next in gravitational wave astronomy? Well, there's this gap. We have never detected any stars of any type, whether they be neutron or black holes or anything else, that are between 2.5 and 5 solar masses. And that's kind of weird. Why not? Why can't a star form that's in this range? So we're not sure if just because we haven't detected them yet, or they just don't exist. See, if they just don't exist, it completely changes the way we think about stellar formation. Because according to, you know, sort of modern day theory of stellar formation, this should be possible. But if it's not, it kind of changes that. Or maybe they do exist and we just haven't been able to detect them yet. So this is sort of the next big goal for gravitational wave astronomy, is to see if we can detect something in that range, which would prove something does exist in that range. More gravity wave observatories, that's another goal, right? And, you know, they're building. There's going to be one in India, there's going to be one in Japan, there's already one in Italy, there's going to be one, I think, in Germany. And these are all getting ready to come online, and it took us like 30 or 40 years, and they're doing it a little faster using some of the lessons we learned building ours. So this is sort of the next thing, is that we're going to have enough of these that the triangulation will be better, that maybe we can get better electromagnetic signals, whether it be visual or infrared or gamma rays or X-rays, that we can keep getting these sort of confirmations of the event, whatever it is, whether it's a neutron-neutron star merger or black hole merger, that we can get some other confirmation that says, yeah, this did really happen. It wasn't just a car driving by next to Livingston. And what do I think is next? Well, I've always felt that anything professional astronomers do, amateur astronomers can do. In fact, I don't know if you know this, but there's been more supernovae detected by this guy in Georgia than like all the professional observatories in the United States, and he's an amateur. And this goes true for comets and lots of stuff that amateurs do. So if visual astronomy has amateur components, maybe next time I'm going to Cherry Springs State Park, Pennsylvania, which is an astronomy park, I'll show up with a little portable interferometer. And I'll detect my own gravity waves. Hey. And that's it. So, are there any questions?